Problem 447. Analytically determine the angular displacement of the wheel assembly and the nose wheel actuation mechanism shown in the figure as the 12-inch crank is rotated from its current position 60 degrees counterclockwise. Okay, so to start this problem, we're going to go ahead and draw our kinematic diagram out. So let's go ahead and trace the figure. So start by tracing all the links of the figure. The links that matter, we're not going to worry about this actual wheel assembly down here because that's really not part of the kinematic mechanism that we're looking at. All right, let's draw our joints as well as our ground connections. We'll go ahead and label everything. So we'll call this A, B, C, and D. And we'll just draw on our ground connections just to be thorough. Okay, so here's our kinematic mechanism drawn out. I think it's also worthwhile if we go ahead and we just label some distances for us real quick. So AB is our 12-inch link. BC is our 30-inch link. CD is our 26-inch link. And AD, we have to do a little work for. So to solve AD, it's real simple. It gives us this 5-inch height and this 32-inch horizontal distance. And we can just use Pythagorean theorem. 5 squared plus 32 squared square rooted is equal to 32.39 inches. So we'll call AD 32.4 inches. Right in our kinematic diagram, let's draw this 15-degree starting angle that AB starts at. So we'll just draw a line off the vertical, and then a line that follows the path of AB. Highlight that, 15 degrees. We're also going to, at point A, we'll draw a line horizontal to give us a horizontal reference frame to look at. We can call this angle in here, we'll call this angle beta. So as we're going to look and try and figure out the motion of this, we're going to try and break this down into triangles and get the position of things so that we can find the angular position CD, and we're going to see how the position angularly of CD changes as the 12-inch link changes. So the first thing we're probably going to want to look at is probably get this reference angle beta just to get us a start point of how AD is oriented. And that's simple enough because we have our given 5 inches and 32 inches. So solving beta is nothing more than the inverse tangent of 5 over 32. And that gives us beta equal to 8.9 degrees. So if we're looking at this, again, it's probably worthwhile to know this angle right in here that comes off of joint A, right, the angle DA and AB make. We'll go ahead and call this angle phi. So if we're looking at solving phi, we can see that this horizontal that we've already drawn, and if we continued our vertical down, well, that would be 90 degrees. And then we have our 15 degree angle. So we have 90 plus 15. We can subtract beta off that and we can find phi. So let's go ahead and let's do that now. So phi is equal to 90 plus 15 minus beta, which is 8.9. Which gives us phi is 96.1 degrees. So as we're continuing, as we remember what we were learning in this chapter, what we're going to want to do with problems like these is just break it down into triangles, because we know how to solve triangles, right? We've done a lot of trig in the past, so triangles are relatively easy to solve. So if we were going to try and break this down to triangle, let's draw a line between B and D. So essentially what we've just done is broken our kinematic mechanism down into two triangles that we're able to work with now. So if we wanted to know the length BD, well, how would we go about doing that? Well, we know the length AD, and we also know the length AB, but we also know this angle phi, so we could use the law of cosine. So the law of cosine being a squared is equal to b squared plus c squared minus 2bc cosine of angle A. So let's write that out. So law of cosine is a squared equal to b squared plus c squared minus 2bc cosine angle A. So let's use the law of cosine to solve for BD. So BD is equal to AD squared plus AB squared minus 2 AD AB times the cosine of our angle phi. All that square rooted. So BD is equal to 32.4 squared plus 12 squared minus 2 times 32.4 times 12 times the cosine of 96.1. All under square root. That gives us BD equal to 35.7 inches. Okay, so now we have BD, so let's try and complete this triangle up top. So another angle that will probably be of interest to us, especially because we're looking for this total, right? What we're really focusing on is CD and where CD is oriented. So another angle that's probably of interest to us will be this angle right in here that we're going to call theta. Now, to solve theta, if we're looking at what we know in this triangle, so we know the length AB. We also now know the length BD. And we know this angle phi, so we can use the law of sine for this. So the law of sine, states that the sine A over length A sine A over length A is equal to sine B over length B. So let's apply the star problem. BD over sine phi is equal to AB over sine theta. So 35.72 over sine theta is equal to 12 over 96.1. And this gives us theta equal to 19.5 degrees. All right, so now let's look at trying to solve this bottom triangle. We're going to have to move to another sheet, so I'm going to go ahead and copy this over. And I'm going to copy our lengths over as well. And our two angles, just write those down. Phi equal to 96.1 degrees, and theta equal to 19.5 degrees. So let's look in solving the other angle down here. We'll go ahead, we'll call this angle alpha. So if we were to solve alpha, what are we looking like we're going to be needing? Well, we have two lengths on this triangle. and we're looking for, we have all three lengths on this triangle. So we can go ahead and do some manipulating with the law of cosine, and we can say that alpha is equal to cosine inverse of CD squared plus BD squared minus BC squared over 2 CD BD. And you see that's just a manipulation of the law of cosines, so that we're solving for the angle now instead of solving for a side. So if we go ahead and plug our values in here, alpha equal to the cosine inverse, 26 squared, plus our BD, which is 35.72 squared, minus 30 squared, all that over 2 times 26 times 35.72. So this gives us alpha equal to 55.5 degrees. And to get the actual, right, what we're solving for is this orientation of this line CD. So quite simply, this overarching angle, we can go ahead and call this, we'll call it psi. So overarching angle psi is equal to theta plus alpha, which is equal to 19.5 plus 55.5, which gives us 75 degrees. So now we have our starting displacement, right? So what we've done, we've gone through and we've looked at how this mechanism is oriented originally, and we found this angle that this bar that's attached to the wheel is currently located in relation to our imaginary ground line AD right there. So now what we're going to have to do is we're going to have to move this mechanism, right? This 12-inch bar is going to rotate 60 degrees counterclockwise. It's going to move up like so. And we need to figure out in which way this bar is oriented now. So let's go ahead and write this out. AB is rotated 60 degrees. So if AB is rotated 60 degrees up, AB is rotated 60 degrees clockwise like so. Our angle phi is going to get bigger by 60 degrees. So phi prime, right, because we're looking at it in our second configuration, so phi prime is equal to phi plus 60, which gives us 156.1 degrees. And now we basically just need to run through the calculations we just did, only with our new values. So we're going to jump into the law of cosine to try our new length, to find our new length for dB as B has been rotated. So now we're solving for B prime D, which is equal to AD squared plus A B prime squared minus 2 AD AB prime cosine of phi prime. All this under a square root. So B prime D is equal 32.4 squared plus 12 squared minus 2, 32.4 times 12 times the cosine of 156.1 degrees. And we'll find that B prime D is equal to 43.63 inches. Again, our next thing to try and solve to complete our top triangle will be this theta value. So if we go back to solve theta before, we used the law of sine, so we'll use it again. So B prime D over the sine of phi is equal to AB prime over the sine of theta. So 43.63 over the sine theta, sine phi rather, is equal to 12 over sine theta. We know our phi value, so let's actually go ahead and write this in here. Phi is 156.1. And that gives us theta equal to 6.39 degrees. Okay, next step will be solving for alpha. And alpha is again just shifting around our cosine, our law of cosines. So alpha prime, again this is theta prime, theta prime, theta prime, phi prime. So alpha prime is equal to the cosine inverse of C prime D squared plus B prime D squared minus BC prime squared over top 2c prime d times b prime d. And this gives us alpha prime equal to 42.28 degrees. So our psi prime is equal to our phi prime and our theta prime. So theta prime is 6.39 degrees plus our alpha prime, which is 42.28 degrees. So psi prime is 48.67 degrees. Now, to finish the problem out, the change in angle psi, or the change in the orientation of CD with respect to the ground AD, right, what we're solving for, the change that CD has been made due to the rotation of AB, the change in psi is equal to, let's move this up a little bit, is equal to psi minus psi prime, which is equal to 75 minus 48.67 and we get that the change in psi is equal to 26.33 degrees. And that is our final answer to this problem.